Hey everyone. Our next lesson is going to be on light and refraction, and specifically how light is refracted when it's traveling through two different medium. And that's going to depend on the angle at which the incident ray is going to be entering the different medium. So we'll look at four different scenarios, how light can be refracted, and ultimately it's going to depend on the angle in which the incident ray is entering the different medium. So we'll kind of highlight the first four scenarios and then we'll look at them visually. So if a light ray in air, so starting in that medium in air, is incident on an interface with water at 0 degrees, the ray of light is going to slow down upon entering the more dense water, but it is not going to change direction. The second one we'll look at is when a light ray in air, so again, originating in air, is incident on an interface with water, so from a less dense medium to a more dense medium, at some angle, the incident ray is refracted towards a line that we know now is called the normal. The third scenario is when a light ray in water is incident on an interface with air, or from a more dense medium to a less dense medium. Again, at an angle, the incident ray is refracted away from the normal. So depending on if we're going from less dense to more dense, the incident ray will be refracted towards the normal, or from a more dense medium to a less dense medium, the incident ray is refracted away from the normal. And again, we'll look at that visually in a second. When a light ray in air is incident on an interface with water at 90 degrees, the ray of light does not change direction. And we'll see what each of these means visually. So the first scenario, what we have is a light ray in air incident on an interface with water at 0 degrees. So let's call this upper portion of this circle air and the lower portion water. And we'll keep this the same orientation for the next three examples. The top part being air and the lower half being water. So if we have a source of light at 0 degrees, and it's shining a ray straight through the two medium from air to water, and we'll label this. So this is the incident ray originating from the source, and this one is the refracted ray, but it's a ray that's not refracted. And that's due to the 0 degree angle upon which that incident ray is moving from the air to the water. Now I'm going to highlight a couple variables here. And I want you to remember from our equation, velocity equals the frequency times the wavelength. In these scenarios, we're going to have a frequency that remains constant, which means the relationship between velocity and wavelength is direct. So when velocity increases, wavelength increases, and vice versa, as long as the frequency is constant. So in this scenario that we just looked at, scenario A, the velocity of that light ray in air is greater than the velocity of the light ray in water. You know, the frequency in air is the same as the frequency in water, and because of that, the wavelength in air is greater than the wavelength in water. So at 0 degrees, our light ray is not refracted at all when moving from air to water. Now in the second scenario, each of these little hash marks is indicating an angle of 10 degrees. So let's say we put a light source somewhere about 40 degrees. We're going to shine this ray towards the boundary between air and water. And remember, this upper portion is air and the lower portion is water. So our interface for each of these, I will do this in a little blue, and I'll keep this here. We'll do a little wave of water along here so we can see this a little bit better. That light ray, as it goes from air to water, which is going from a less dense medium like air to a more dense medium like water, when this occurs, this ray, instead of traveling straight through here, it gets refracted towards that normal line, right? Which is our line that's perpendicular to the interface of our two medium. So this light ray gets refracted towards the normal line. This here is what we'll call theta 1. And this angle here is theta 2. And these two are related to each other. So again, this is our incident ray originating in our air medium. And this is the refracted ray. And this is a smaller angle than the incident ray. And in this scenario, the velocity in A, or in air, is greater than the velocity in water. The frequency in air is equal to the frequency in water. And the wavelength in air is greater than the wavelength in water. So the key here with this scenario, when moving from a less dense medium to a more dense medium, our rays get refracted towards the normal, or the line that's perpendicular to the interface of our two medium. Now in the other direction, so we'll keep this the same. The top half will be air, and the lower half will be water. And just to kind of touch base here in part B, this theta here, I said here that it's going to be a smaller angle than the incident ray. So if this was a 40-degree angle here, this one's going to be less than 40. It's going to depend on the medium what the actual angle is. So in C, we'll consider a light source. Let's say from about the same thing, 40 degrees. And we have our incident ray moving towards our boundary. So the incident ray is originating in a more dense medium and it's moving to a less dense medium like air. The refracted ray, try and make that look maybe a little bit more exaggerated than it actually is. We have two angles here, and both are in relation to the normal. Our incident ray originates in the water, and it leaves our boundary, which we'll color this here. I'll do the last one. So it moves from water into air, and the second angle there of the refracted ray angle 2 is larger than angle 1. So angle 2 is larger than angle 1. And depending on that angle, or that angle is going to depend on the medium in which it is moving through. Wouldn't have to be necessarily just air. It could be something passing from water to, let's say, oil, which would be less dense than water. So in this scenario, the velocity in water is less than the velocity in air. This is the velocity of our light ray. The frequency in air is equal to the frequency in water. And therefore, the wavelength in water is less than the wavelength in air. And this would be true for any rays moving from a more dense medium to a less dense medium. In the last scenario, we're going to look at a light source interacting at an angle of 90 degrees. We're going to have a light ray moving along this boundary at 90 degrees. And we're going to have no refracted ray. So kind of the same idea that we would have with an incident ray at 0 degrees. So the key with these really are B and C, depending on how the incident ray is moving through medium and their density, and how they're going to be refracted either towards the normal or away from the normal. And a good example of this is somebody that might be watching a sunset. I'm going to do my best to draw this. So the person standing here is looking at the sun set over the horizon, but the sun is not actually in the spot where the person thinks it is above the horizon. Because of light refraction, moving from a less dense medium to a more dense medium, the sun's rays, so this is the actual position of the sun. This is the perceived position of the sun. So the actual sun's rays, I'll change the color here so we can see this. If this is the atmosphere here, and this is Earth, the surface of Earth, the light rays are moving. And I'll see if I can draw this appropriately. These are going to bend toward the normal. In this case, the normal is the horizon. So these rays, and this is refracted, the sun's rays, the sun is already set and gone past the horizon when we're seeing it starting to set. And that's because those rays are being reflected, or refracted, towards the normal, as we see here in scenario B, refracted towards the normal, moving from a less dense, the vacuum of space, to more dense, the atmosphere of Earth. And therefore those rays make the sun look, and these two lines here should kind of line up. And that's why we see the sun look like it's above the horizon when it's setting, when it's actually already set. Now, the absolute index of refraction is the ratio of the speed of light in a vacuum to the speed of light in a material medium. And this is given to us by the equation of C over V, and this is found on your reference table. This can be rearranged to solve for the speed of light as the index of refraction times the velocity in the material medium. Now, for comparing two media, we can use a couple different equations, and these are on your reference table. As the ratio of N2 to N1 is equal to the velocity of 1 over the velocity of 2 equal to the wavelength of 1 over the wavelength of 2, or we can reverse that, N1 over N2 equal to V2 over V1 equal to the wavelength of 2 over the wavelength of 1. And this is if we're comparing two different media. Now, Snell's law is what we'll use a lot in regards to refraction of rays. And this is a mathematical relationship that governs the refraction of light as it passes obliquely. This means at an angle, not 0 or 90, from one medium to another of different optical density. So we have to have different media with different density in order for this to occur. And this equation, found on your reference table, is N1 times the sine of the incident angle equal to N2 times the sine of the refracted angle. We can also see this written as the ratio sine of angle 1 over the sine of angle 2, which is equal to N2 over N1. Again, if we're comparing index of refraction between two different media. So we'll use this equation to determine if we know the index of refraction of the two media, N2 and N1, and we know the angle of the incident ray, we can find the angle of the refracted ray as long as we know what the media are. Now, the last thing I'm going to touch base on here is the electromagnetic spectrum, which I'm just going to touch base on this briefly because we've all had a fair amount of experience with this before. So light waves are electromagnetic waves, transverse waves, which consist of periodically or regularly changing electric and magnetic fields. They move through a vacuum at a speed of 3 times 10 to the 8th meters per second. And any electromagnetic wave, any type, regardless of the frequency or wavelength, are produced by accelerating charged particles. So charged particles that are in motion, increasing, decreasing velocity, changing direction, are all going to affect their acceleration and therefore produce electromagnetic waves. So the electromagnetic spectrum contains the complete range of frequencies and wavelengths of electromagnetic waves. We should all be pretty familiar with this. We only see the visible portion here in between 10 to the minus 7th and 10 to the minus 6th wavelength of light. Otherwise, what we know as 4 to 500 nanometers, or 4 to 750 nanometers, depending on the color of the radiation. Decreasing wavelength means increasing energy. So our strong forms of electromagnetic radiation are gamma rays, X-rays, and ultraviolet rays. And longer wavelength are lower energy, like radio waves, microwaves, and infrared waves. And I gave you a little blurb here on the different types, so you guys can read through that. If you have any questions on this, make sure you let me know or bring them up together with class. I hope everyone has a fantastic day.